Notes for section 8.3 are on the topic of growth and decay models and logistic growth. We start with simple growth and decay models. They are generally given in the form y prime equals ky or dy dt equals ky. If we look at dy dt equals ky, we separate the variables, so we get 1 over y dy equals k dt. Then we integrate both sides. We'll get natural log of absolute y equals kt plus c. If I exponentiate both sides, I will get absolute y equals e to the kt plus c. And we're going to rewrite the right-hand side. And remember that now we have an exponential on the right. That means the left side we know will be positive, so we can remove the absolute value bars. And we will rewrite the right side as a product of e to the kt times e to the c. If you recall, we like to replace e to the c with one variable, and we were using capital A for that. So capital A times e to the kt. If I think about when time equals 0 and I substitute that in, I get this result, and e to the 0 power is 1, so that means the right side is just a. That means y of 0 equals a. Y of 0, that's the value of y at time 0, so at the starting time. Therefore, that capital letter A is considered the initial value of the function. So it might be more appropriate to write it this way. When given the differential equation dy dt equals ky, you can count on the solution to that differential equation being represented in this fashion. So let's work on an example using that formula. In 1950, the population of the world was 2,560,000,000 people. In 2000, the population of the world was 6,080,000,000 people. What is the growth rate? What is the population in 1993? What will be the population in 2020? I guess we could actually check that answer. I probably wrote this question a while ago. This is what I want to do. I want to let t equals 0 represent 1950. So time 0 will be 1950. What I need to do is set up a differential equation. This is the rate of the population growth. So I'm going to use a capital P for population. dp dt equals kp, where p of 0 equals 2,560 million people. We can work without the extra zeros. I do not need to go through, separate, and integrate to find the solution to this differential equation. I know the solution to the differential equation. It will look like this. P of t equals 2,560, because that's the initial amount, times e to the kt. So the task for me would be to find k first, and then I'll have the complete formula, the complete model for population growth based upon that initial condition. Let's substitute in another piece of information we were given in order to do that. We were given the population in the year 2000. So that's 50 years after our initial condition. Therefore, we have P of 50 being given to us. And in millions, it's 6,080 million. So P of 50 is 6,080. Let's substitute that into our equation. So the population is 6,080 million equals 2,560 times E to the k times 50. I'll divide by 2,560. That gives me 2.375. Then I'll have to take the natural log of both sides. Remember taking the natural log on the right? The natural log of e to a power is just that power. So that's how we get 50k out of the exponent. Let's use our graphing calculator now. type in natural log of 2.375, be sure to close the parentheses, and then divide by 50. You should get K is about 0.0172999. Now, I don't want you to just write that down. I also want you to store it in A on your calculator, because we're going to use that value later to answer the other questions. So what that means, our result, is that the growth rate is about 1.7% per year. So we've answered the first question, what is the growth rate? Next, we want to look at what the population would be in 1993. So let's get the model for our equation. We have a value for K. It is stored in A. So you could do this. You could write P of T equals 2,560 E to the AT. I keep circling the A because that's my symbol to remind myself I have it stored in A on the calculator. To check the population in 1993, I need to remember what value of T would represent 1993. Since T equals 0 in 1950 and 1993 is 43 years later, then I'm going to evaluate this function for T equals 43. Enter that into your calculator, 2,560 times E to the stored A times 43. Your answer is about 5,387. What will be the population in 2020? This question is written like this because I had written the question before 2020. What will T be in 2020? T would be 70. That's 70 years after our initial condition. In your calculator, you just need to hit second enter and you'll get the equation back again and type 70 over the 43 and you will get 8,593. So that means the answer is 8,593 million. I think I didn't say that up here. This was 5,387 million. 2020 we would predict 8,593 million based off of this model. And I looked it up. Actually, the population was 7,585 million. So I would say we need to revise our model. Our model was based upon data from 1950, so we need to use some more recent data to come up with a fresh model. A topic special to BC Calculus is logistic growth. Logistic growth is a more accurate model for working with population. The size of a population often increases exponentially in its early stages, but levels off eventually and approaches its carrying capacity because of limited resources. So the rate of change of a population in this case is a little more involved than the model we were using up above. We've written dp dt equals K times P times the quantity 1 minus P over M. The K is still the growth rate, so we wrote that here. P is your population, and then M is going to represent carrying capacity. We are going to give you the solution to the differential equation. M, which is the carrying capacity, so that's as big as the population can get, over 1 plus A times e to the negative kt. You see K is in there. The growth rate is in the solution to the differential equation, and we have this constant A back again. But in the logistic growth model, A is represented by this calculation. So you're going to take the carrying capacity minus the initial population divided by the initial population. Let's just practice with that information first before we do a full example. Here is a logistic curve. This is a solution to a differential equation. P equals 600 over 1 plus 4 e to the negative 0.02 t. Can you pick out all of the information from that solution? The big number on top, the 600 number, that's M. That's your carrying capacity. The value of K is 0.02. You don't want to put negative there because look back up in the formula. The formula comes with a negative in front of K. What is the value of A? Well, that's your coefficient of E. So the value of A is 4. Okay, so just practicing looking at the solution. And you'll need to memorize how this solution is set up. So you'll need to memorize this information at the top of the page. And we'll just keep practicing to help you remember. In the next example, I'd like to make it a little more interesting and give you a differential equation, and we will build our solution from that information. First of all, I'm going to remember what these numbers represent. So I know dp dt is the name of the differential equation. 0.7 is the k times the population times 1 minus the population over the carrying capacity. That's the formula from the previous page. We have an initial condition also. Carrying capacity, that's the number in the denominator. So 100 is the carrying capacity. The value of k is 0.7. And now we need the value of a. You're going to have to calculate that because that wasn't handed to us. What actually was handed to us was the initial population of 10. We're going to need that number. Do you remember that A is the carrying capacity minus the initial population over the initial population? Carrying capacity is 100. The initial population is 10. Perform this calculation and you get 9. So the value of A is 9. And now let's write the solution to the differential equation. We'll write our solution as P of t, and remember that's a fraction. The carrying capacity goes in the numerator. The denominator is of the form 1 plus A times e to the negative kt. 1 plus A is 9 times e to the negative kt. That's the solution to this differential equation. Since this is our first look at a differential equation and its solution in our work, I want to take a look at those things on the graphing calculator. Let's switch over to the graphing calculator and see what they look like. First, I want to type in the differential equation. Click on Window, set your min to 0, set your max to 100. I'll choose an X scale of 10. Choose a min of 0 and a max of 30. I'll choose an Y scale of 10 and hit Graph. We have this upside down parabola. Let's look at where the maximum is occurring. So the maximum is occurring at 50, 17.5. Remember, our input variable was P, the population. So the population is at 50 when the rate of change is at its greatest. So if you are being asked about the population, they might say, what is the population when the rate of change is at its greatest? And that's happening at the maximum on this first derivative graph. Remember, this is from a differential equation, so this is a first derivative graph. Now let's look at what the solution looks like. I'll turn off the graph of the differential equation, and I'll set up a new graph for the solution to the differential equation. The window for this graph can be changed to X min is still 0, X max is 30, Y min is 0, Y max is 130. This is the solution to the differential equation. Notice how it starts off exponential, like we learned in the notes. In the beginning, it's exponential, but eventually it tapers off. Do you remember carrying capacity of this differential equation? It was 100. Let's enter y equals 100 for y sub 3 and look at our carrying capacity. So you can see that our graph is quickly approaching a carrying capacity of 100. Now, what about the first graph that we saw? We saw the differential equation graph and we looked at the maximum on that graph. Where did we say the population would be when the rate is at its highest? We said that would occur at P equals 50. If I draw that line in, P equals 50, graph, it happens at the point of inflection of this graph. Did you notice how this is concave up over here, and then it switches to concave down? So the point of inflection is where the rate of growth is at its fastest. The third example on this page, I give you a logistic differential equation, but it doesn't look like a logistic differential equation. Remember, in the parentheses, we would normally have a fraction in there. So the problem is the 150 is in the spot where we would normally have a 1 in that formula. The easiest thing to do is just factor out the 150 from the parentheses. The equation will look like this then. dp dt equals, when I take out the 150, when I factor it out, I'm going to multiply it times this decimal, 0.0002. That is not k. That is not your k because the rest of the right side doesn't look like it normally does. That's going to get multiplied times 150, and you'll get 0.03. The variable p is still on the outside of the parentheses, but now, since we factored out 150, there's a 1 in the first position of our parentheses. However, if we factored 150 out of the first term, we have to factor 150 out of the back term. So we'll get p over 150. Now our differential equation is of the form that we could pick out our k value and our carrying capacity value. In fact, carrying capacity is sitting down there in the denominator, 150. The value of k is now obvious. It's 0.03. And then let's calculate the value of a. So remember, for A, we have to take the carrying capacity and subtract the initial population. 20 was given as the initial population, and divide by 20. You should get 6.5. Now we have all the numbers we need to set up the solution to the differential equation. P of t equals 150 for our carrying capacity over 1 plus A is 6.5 times e to the negative 0.03 t.